Alrighty, friends, welcome to the 25th lesson of Math 222 at SUNY Geneseo. Glad you're along for the ride. Glad you're still here. On today's show, we take a look at one of the more important tests that we look at for convergence of infinite series. This one is called the ratio test, and it looks like this. Let the sum of the ANs be a series of positive terms. We're still not going to let negative terms in, not till our next lesson. And suppose that the limit as n approaches infinity of the n plus 1th term over the nth term is some number rho. Then the series converges if rho is less than 1 and diverges if rho is greater than 1. The test is inconclusive if rho is 1. I gotta let that sit there for a minute, and you gotta think about that. Where have we seen this kind of language before in our study of infinite series? Well, this is the ratio of any term to the one before it. What is the other kind of series that we studied where we look at the ratio of any term to the one before it? This mocks up geometric series. You remember what we called the limit of a geometric series, what we called the ratio, we called that r. Well, this is the Greek letter rho, and it makes the R sound. And that choice is deliberate because the ratio test makes a clear connection to geometric series. So here's what's really going on. If you have an infinite series and you look at these guys, and these guys start looking geometric, maybe way out there. Maybe way out there at the 11 billionth term, it starts looking geometric. Then the rules for geometric series convergence apply. And you converge if the ratio is less than 1, if the terms are getting smaller in a geometric way. The series diverges if rho is greater than 1, because for this to happen, the n plus 1th term has to be bigger than the nth term in general as we get out there. This is the tricky part. If rho is 1, then the ratio test gives you no new information whatsoever. It is not helpful. This is a difference from our work with geometric series. If you have a geometric series and the ratio is 1, we know that that series diverges. That is not necessarily true with the ratio test. So, time to play everybody's favorite game. Does it converge? Here's a sum. N goes from 1 to infinity. 3 to the n plus 5 over 5 to the n plus 1. I want to know, does that series converge? I would like to use the ratio test. And to do the ratio test, we need rho. We need rho. And that's the limit as n approaches infinity of the n plus 1th term over the nth term. So there's rho. It's the limit as n approaches infinity of the n plus 1th term over the nth term. Time now for a little bit of algebra. I don't think this step is the step that's going to crush you. Just moving denominators around. as I am allowed to do. Still nothing earth-shattering. I kind of have the sense that this goes to 3, and I kind of have the sense that this goes to 1/5, and sure enough, it does. We could divide everybody over here by 3 to the n plus 1. And we could divide everybody here by 5 to the n plus 1. And we can take a look at what happens as n gets large. As n gets large, this goes away, this goes away, this goes away, this goes away, and you end up with 3 times 1/5, and that's 3/5, which is less than 1. And so this series converges because ultimately it looks like a geometric series of ratio 3/5. So the ratio test confirms this series converges. You may well argue, hey, wait a second, coach. Couldn't we just do a comparison test with that? Right? Sure you could. I know you. I spent 5 seconds listening to you yell back at me. That's the way I would have done it. Great. Sure you could do a comparison test with this series. The limit comparison would turn out to be that these series behave the same way. I know that this is geometric with a ratio less than 1, absolute value less than 1, and so this series will converge by comparison. So it makes you wonder, well, what do I need the ratio test for if the comparison test will do it for me? And there you go. You may recall that this does not mean that n is excitable. This means that this is the product n times n minus 1 times n minus 2 all the way down to 1. So I'm wondering, does this series converge? And we're going to use the ratio test to see if it converges. We're going to compute rho. It's the limit as n approaches infinity of the n plus 1th term over the nth term. So what does that look like? Well, I know that 4 to the n and 4 to the n plus 1 leave you with a 4 in the numerator. I know that this is n plus 1 times n minus 1 all the way down to 1. And this is n times n minus 1 all the way down to 1. So all of these drop out with all of these, and you're left with n plus 1. So this is the limit as n approaches infinity of 4 over n plus 1. And guess what that is, friends? Right. And guess what? That's less than 1. This turns into a geometric series where basically all the terms zero out. And therefore, this series converges. All right, so anything with a factorial in it converges. Well, sort of, I guess, a little bit. Not really. Right? Like, what in the world is that? What in the world is that? So, again, I want to use the ratio test, and I want to compute rho. It's the limit as n approaches infinity of the n plus 1th term. Notice how I did that. The n plus 1th term over the nth term. Notice the copy change flip there. So what happens to this? Well, we know from the previous example that n factorial and n plus 1 factorial leave you with that. What happens here? Well, this is 2n factorial. This is 2n plus 2 times 2n plus 1 times 2n times all the way down. So this leaves us thusly. So this is the limit as n approaches infinity of 4n squared blah 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 over n squared blah blah blah, and that's 4, which is bigger than 1. This series diverges. Okay, so I sort of understand kind of a little bit. One more would be super helpful. How about this one? 3n factorial over 27 to the n factorial, n plus 1 factorial, n plus 2 factorial. I don't even know what to think about that. Here, we're going purple. I just don't know what to do with that. Consider the limit as n approaches infinity, then you have this mess, the n plus 1th term. So the n plus 1th term would have 3n plus 3 factorial, 27 to the n plus 1, n plus 1 factorial, n plus 2 factorial, n plus 3 factorial, then divided by the nth term. So divide by the nth term. Denominators become numerators, and numerators become denominators, multiplying by a reciprocal. So now what happens? Well, I'm pretty sure that this and that leave us with 27. I'm pretty sure that these just cancel outright. I'm pretty sure that this n factorial and this n plus 3 factorial are going to leave us with this. And I'm pretty sure that this is going to cancel out with that and leave us thusly. So let's see if we can figure out what's happened. The numerator is 27n cubed blah blah blah. The denominator is 27n cubed blah blah blah. In fact, I'm not sure if that series converges or diverges. I don't think I have a test that tells me if that series converges or diverges. I know that the ratio test is inconclusive. So time for you to play. And this is where we will pick it up when we gather, looking for the sum as n goes from 1 to infinity of n plus 1 over n factorial, and the sum as n goes from 1 to infinity of 3 to the n over n cubed times 2 to the n, and we'll see what happens with those. Okay? So, hey, I did it in less than 15 minutes. You're my heroes, which means you have an extra 15 minutes to play around with this and still get a half hour of good math in. Can't wait to see you next time. Okay, bye.